Hello everybody, I am Chaitra Desai, research scholar from Keli Technological University, India. I am glad to present our work on Aquagan, restoration of underwater images. This is a joint work carried out with Sai Sudhir Reddy, Ramesh Ashok Tabib, Ujjwala Patil and Uma Mudin Gudi. Underwater image restoration is a potential problem for determining submerged resources. Researchers aspire to capture high quality underwater images for inspections of marine archaeology, coral reefs, aquatic life, flora, and fauna. Capturing high quality images underwater is a challenging affair as underwater images suffer from low contrast, color cast, and haze due to dynamically varying properties of the water. The light reaching the object from the surface is subjected to direct scattering and backscattering, resulting in a degraded image. Direct scattering and backscattering introduces color cast and blur and haze as shown here. This motivates us to restore the degraded observations to recover its true colors and the lost information. Restoration using deep learning algorithms demands degraded observations coupled with ground truth information. However, obtaining the ground truth information in underwater scenario is not feasible. Towards this, we propose to render synthetic underwater images considering revised image formation model for modeling the deep learning based frameworks. In this slide, we present the contributions which we have made towards this work. We propose an Aquagan to recover the true observations from the degraded observation. Towards this, we estimate the attenuation coefficients and give them as a clue for training Aquagan. We propose a composite loss function while modeling an Aquagan. We compare the results of the proposed methodology on benchmark dataset with the state-of-the-art methods. This is the overall framework which we have designed towards rendering of synthetic underwater images. As discussed, obtaining the degraded underwater images coupled with ground truth information is quite challenging in underwater scenario. Towards this, we consider to render synthetic underwater images. We consider the image formation model as proposed by Daria et al. To render the underwater images. However, the image formation model is sensitive to the spectral response of the camera, the irradiance, the reflectance, and the depth. We estimate these attenuation coefficients and give it as a clue for rendering algorithm. The rendered images can be further used to train deep learning frameworks. This is the overall proposed framework called as Aquagan. In this slide, we discussed about the proposed framework for restoration of underwater images and term it as Aquagan. Aquagan is modeled to restore the degraded observation considering Gerlo patch as a clue. Initially, we estimate Gerlo patch with unit-based autoencoder and provide it as a clue for training Aquagan. Aquagan is modeled with a combinational loss function to learn mapping between the degraded underwater image and the corresponding restored image. The estimated Gerlo patch for corresponding degraded underwater image will act as a clue while training the Aquagan. Here we present the estimations of Gerlo patch, that is AC infinity, also called as atmospheric light. This estimated Gerlo patch will act as a clue while training Aquagan. The first row corresponds to the degraded underwater image on UIBD dataset. The second row corresponds to the estimation of Gerlo patch, that is AC infinity, also called as atmospheric light. The regions highlighted in red indicate the degradation which is caused due to the scattering of atmospheric light. This is the overall framework of proposed Aquagan. As discussed previously, the estimated Gerlo patch is given as a clue while training the framework. The degraded underwater image and the estimated Gerlo patch is given to the unit-based autoencoder. The generated latent space from the estimated Gerlo patch and the degraded underwater image is concatenated. The concatenated latent space is further provided to the decoder to decode and generate the restored image. We have modeled content loss and style loss to learn the mapping between the restored image and the corresponding degraded underwater image. To generate the restored image, we have experimented with several combinations of loss function and we have arrived at a composite loss function using a combination of content loss, style loss, and a binary cross entropy loss. To arrive at this loss, we have experimented with several other loss functions a combination of SSIM and MSC with PSNR of 14.9 and 0.38, a combination of SSIM and MSC again with different alpha and beta values, and we have arrived at a PSNR and SSIM of 11.6 and 0.26, and a combination of style loss SSIM, style loss and content loss. Having done several experiments, we came up with a combinational loss function where style loss, content loss and binary cross entropy loss gave us a remarkable growth in PSNR and SSIM. Keeping this as a benchmark, we trained Aquagan. The results on synthetic data is shown towards your left hand side. The first column corresponds to the rendered synthetic underwater image with respect to each experiment, and the second column corresponds to the restored underwater images for the respective experiments. Here we present the results of restoration on synthetic underwater images. The first column presents the ground truth information. The second column shows the rendered synthetic underwater image at 5-meter depth. The third column shows the restored underwater images using the proposed framework Aquagan. The fourth column shows the rendered synthetic underwater images at 9-meter depth. And the fifth column shows the restored underwater images using the proposed framework Aquagan. We have also tested the framework Aquagan on real underwater images on the benchmark dataset called UIBD. First row here corresponds to the images from UIBD dataset. The second row shows the results of restoration from Chongili et al. The third row shows the restoration results of the proposed framework Aquagan. The quantitative scores for each of the images is presented below. In this slide, we present the conclusion of the overall work. We have generated the realistic underwater image to model the deep learning frameworks. We have also modeled Aquagan to learn mapping between the rendered synthetic underwater images and the corresponding ground truth image. We have experimented with different loss function and have come up with a combinational loss function. We have demonstrated the results of restoration on both synthetic data as well as real data. We have compared the results using quantitative metrics on benchmark datasets with state-of-the-art methods. Thank you. For any queries, you can contact us at sevi@klitech.ac.in.